single LC circuit and check the parameters. And ideally, if I had two independent LC circuits, then I would just get this. This resonance. Yeah. So I did that. I think that's the simulation which is called a two-mode upper. It's a little bit annoying that Okay, I have to always just quit the presentation. Maybe I'll not go into the presentation mode anymore. So if I let's just open this upper one. Okay, so just to visualize. No, I don't want currents. Okay, sorry, I'm in the current viewer, so let's go into the project, open, upper. Okay, so the only thing I did was I deleted all this, this inductor and the bottom plate of the capacitor. So in principle, I should get the resonance 1 parameters. Okay. So now if I view the response, I do get the resonance. But okay, remember, originally we had a 5.6 gigahertz, and now this resonance is at 6.5 gigahertz. So there is a big shift in frequency. That's not so good. And also, if I fit the external coupling rate, what I see, and all these parameters are included in your file. What I see is that it's actually 120 or 130 kilohertz. So our original idea was kind of good, that this circuit is much less coupled. But what messes up the thing is that when you put everything together, it doesn't act independently. Okay? So, and now if you look, you can play with it a little bit later. If you look at the current distribution, it's very nice. It's just current, of course, in the loop. And there is no charging effect of the feed line. So there's no capacitive coupling purely to this mode. Okay? So yeah, if I just compare this top circuit versus resonance 1, resonance 2, it's somewhere in between. So obviously there is some kind of interaction going on. So I hope that this example is already a good indication that when you design a more complicated circuit, it is worth simulating the entire thing as well as parts of it and see the difference. Because you will see if there is an unwanted or unexpected interaction going on. Okay, so this is the plot I extracted yesterday. Maybe it's a little bit deceiving intentionally, but this is the point that now I'm looking at the lower frequency mode for the entire circuit. I look at the charge distribution, and I see that charges are here. So this creates this capacitive coupling to the feed line. It's not that much, so I think it's about two orders of magnitude less than the charge on the capacitor, which is of course expected. But this is enough to change your resonance frequency as well as your coupling rate. Okay, so now I would like to introduce. So I think anyway in about 5 minutes we would have to stop, and then you will do this exercise. But I quickly introduce a solution. So obviously you cannot stop here, otherwise you don't get a PhD. So so what can we do? And what we did was, okay, let's really change gears. And okay, we really wanted two independent circuits. And the problem was that when one circuit was active, the other part of the circuit was still somehow participating in an unwanted way. So let's change this around, and let's design a circuit where it's intentionally hybridized. So there's an intentional interaction between the two LC circuits, but then we can maybe better control it. So the idea is the following. We have, and this is maybe not the simulation part, but how the simulation can aid your design idea. So now we have two LC circuits again. So this schematic shows one LC circuit and the other with a shared inductor. And one of them will have this mechanical drum type capacitor, which you saw before. And the other one is just a simple capacitor. And now let's design the frequencies of the two LC circuits to be the same intentionally. So then what happens if you couple two LC circuits or two harmonic oscillators with the same resonance frequency? They will split. Yeah? So they will normal mode split, and they will form these modes. I should see some, this is a PDF? No. Okay, so they will form two modes. And in terms of current distribution, what you will see is that one mode will have currents which are flowing in the same direction on in these two loops. And obviously this mode will be highly coupled to the feed line because the current is flowing in the same direction on these coupling inductors. And in the other mode, they will have this opposite direction flowing. So then the inductive coupling from this to this will compensate, will cancel the inductive coupling in the other loop. Okay? So that's kind of the idea. And how you can check it. So for example, for the symmetric mode, which is the bright mode, on this shared inductor, the current will be cancelled because the current, I had these nice arrows, but somehow you can't see them now. So so the current is flowing this way on this loop, let's say, but then the opposite on the other loop, so they will be cancelled. So in the end, you will just have current in this big loop. And so this simulation file, just to check if this is true, is also included. So I'll quickly show it to you. Okay, so this is called hybrid. So this this has the most complicated file name. If you open that, so this is how the circuit looks like. Okay, so you will see these two LC circuits with one drum capacitor, and the other capacitor is just a finger type capacitor. And of course, we did a lot of optimization how to match both the inductances and the capacitances in these two LC circuits. So, and it's kind of funny that this big structure, this big capacitor has the same capacitance as this one, more or less, in principle, because the capacitor, the plates are very, very close. So what we normally extract from the measurement data is that it's a few tens of nanometers. Okay, so now if you look at the current distribution, and maybe I'll just show it in the presentation, it's a little bit easier. Okay. So in this hybridized mode design, what you will see is that you have one mode at a lower frequency, around 4 gigahertz, and Sonnet already shows you that yes, the external coupling rate is in the order of 100 kilohertz. By the way, this is very difficult to simulate without this enhanced resonance detection, which we didn't know before, so we did it, but it takes a lot of time because you can really miss the frequency, and then you really have to mesh, so it takes days to simulate it. So what you see here is that there is basically current everywhere, and actually there is double the current here, which is expected, because in this mode, you have current which is flowing in this loop, this direction, and this in the opposite direction. So here they add up, but the direction here and here are opposite, so the inductive coupling to the feed line is cancelled. Okay? And so the other mode, what you see is that there is no current here, but it's a much larger coupling rate, so it's around 3 megahertz. So this circuit looks promising, and we used it because it does create two modes. They are much, the hierarchy is significant in the coupling rates, and then there is no weird circuit interaction unwanted, which messes up the design requirements. Okay, so this is also included if you want to play with it, or maybe if you want to take it further. And I'll just maybe go to the take-home messages. So the take-home message is that multimode circuits are obviously the future. You should simulate them, because if you don't simulate them, it takes a lot of time to fabricate and to measure, and you'll be very disappointed. So what's important is not just to simulate parts of the circuit and then you say, okay, I know everything, I put them together, it will work. You should simulate parts and then the whole thing. And I showed you this case study, which is 2 microwave modes coupled to 1 mechanical mode. And here you see that this hybrid mode design is the ideal one. Okay, so I'll stop here. So now we have maybe a shorter 35-minute just kind of a free session, so Q&A session with exercises. So I suggest that Nathan gave you these nice kind of introductory examples which you can do. So please do them. And then if you want to play with them, you can. I think this is these are nice examples to really look at the current densities and try to match it with your expectations. So try to maybe form some kind of intuition what you would expect for current and charge distributions and check it with the software. And you don't have to run the simulations because they're already in the Sonnet file, and I think even Sonnet Lite can open whatever simulations you already simulated. Okay, so thanks a lot, and so we will be around, and yeah, please, let's go for lunch on time, so at 12:30, because we will be late for the excursion later. Thank you.